record here. Okay, cool. Yeah, so in this past week, you covered and focused on, let's see, conformations, right? So you've done things like Newman projections and you worked on those. That's the impression that I got from the recordings and the lecture material. Okay. Yeah, this is a fairly specific topic, and it's one that doesn't really it's important because conformations are like substantial, right? The shapes of molecules really affects what they do and how they can do it. Although when I'm thinking about it now, it doesn't come up overwhelmingly. Okay, like it's important because you spend a lot of the time in this course working with ring structures, but there are a few times again where there'll be a question that's like, write the Newman projection of this. It's way more important because you use this information to understand why, like, how molecules like fold and how they take the shapes that they do. Okay. Anyway, that being said, my impression is that you've covered Newman structures, things like gauche and the other one, interaction, that's totally blanking in my mind right now. And then with that, you also covered like axial and equatorial positions on conformations of a ring, right? So that being chair, boat, flip boat, all those conformations of the ring. Okay. Yeah, and then from last week also, which we were kind of still in the process of talking about, you also last week you were covering acids and bases, which is still an important topic, and we still have a couple of problems from last week which we should go over. Yeah. Okay. So why don't we I'll actually start with the problems, some of those leftovers from last week, because well, those acid and base problems, even though yes, you had your quiz on them, they are important. They're not going to go away. Those questions aren't going anywhere. You're going to need them all the time. Okay. So why don't we go through some more of those? And I'll actually, yeah, I think I can get away with sharing this. Okay. You see this? Yeah. Okay. I wrote my email. Whoops. Now you can't see it. I wrote my email up here. So, email me if you have questions and things, right? Some people were trying to get in touch with me last week and realized that I did not mention how. So you can use my email, send me an email. You could also send me a Canvas message. I know like 1 or 2 people did that. That's totally fine. If you have questions about like workshop, if you're going to miss it or something, I mean, I'm going to post everything online anyway, but if you have questions and things, you can, ask me and let me know. Yeah. Okay. So let me open. Oh, I guess if I'm only sharing this drawing window, then you can't see whatever the other stuff I'm doing, but that's okay. Right. So I will open up and copy these other problems. Whoops. Oh, geez. Here we go. Okay. So as on monitor. Yeah, okay. Here we go. Okay. So the question again was to rank them in terms of acidity or basicity, but in this case, we're just dealing with acidity, right? Because it's all pointing at hydrogens. Okay. So let's take a look at these things. Okay, here we go. We have a couple, for this first problem, there's a few things going on, right? So we're changing the molecule that is attached to, okay? So in most of these cases, it's an oxygen, but here's a nitrogen, right? And once we got this oxygen here, then we have this group over here. We have this carbonyl, which would make this a carboxylic acid. So hint, hint, that's probably more acidic. And then once we have this carboxylic acid, we're adding fluorines, okay? So maybe let's just compare these two first. And what we'll see is that, okay, over here we have these fluorines, here we have these hydrogens. So the difference being that these fluorons are electron withdrawing, okay? So they pull electrons away. meaning that you wind up getting some of the inductive effect here. Okay. And if you'll remember, having electron withdrawing things makes something, let's see, more acidic, and having electron donating things makes them less acidic. Okay, fluorines are electron withdrawing because they're so electronegative that they pull electrons towards them all the way across this molecule. Okay, so this is inductive effect. Okay, comparing here, and the inductive effect is a really weak effect. Okay, I don't remember the actual numbers for these, but it's less than like, this is probably a pKa of around like 4, and this is probably around 3 or something, right? I mean, I don't remember the numbers exactly for certain, but it's something around like that size of a shift. It's not crazy. Yeah, you'll see this acid again maybe like the last day or two of the course, but otherwise they're roughly similar in terms of acidity. Okay, and then, well, the difference here is kind of more substantial, right? Here we have this carbonyl. So when this oxygen becomes negative, you can move that negative onto this bond and move this double bond up to this oxygen. Okay, so here we have the differences because of resonance, and resonance can really make or break an acid here. That's a much more substantial difference than the inductive effect, at least. All right. Oh dear, where did it send me? There we go. Okay. Okay, and then lastly, if we compare these two, well, here's the difference between an oxygen and nitrogen, right? So this is totally different atoms. This will make a huge difference on how acidic something is, right? And oxygen is way more electronegative than nitrogen. Maybe not way more, but when it comes to comparing acids and bases, it's a huge difference. Okay, so nitrogen is going to want to give up its hydrogens way less because that negative charge will be way more uncomfortable on that nitrogen than it will be on this oxygen. Okay, so here we're comparing based on atom or electronegativity. Let's go with electroneg. Okay. All right, which is to say that if this is, let's say, compound 1, and this is compound 2, and this is 3, and this is 4, in terms of most acidic to least, okay, well, we said that this nitrogen is really not going to want to give up its hydrogens, okay? And this oxygen is slightly better than that, but this one over here, number 1, is way better because of resonance, and this one is even better yet because of inductive effect, okay? So we have this kind of like ascending series of numbers. So 4 is the least acidic, and then followed by 3, and then 1 over here because of resonance, and 2 is the most acidic, okay? Because it has resonance and the inductive effect, which is just like the icing on the cake. Okay. Sound good? Let me scroll through the chat. Nope. Okay. Looks okay and good. Yeah, hopefully you got some practice with this earlier, but this is important and good to see again anyway. Okay, and now we have a problem that's on a phenyl ring. So this is like, you're gonna see phenyl rings all the time, and this sort of thing, this sort of acidity question is pretty important because eventually a lot of the chemistry you'll be doing is on these rings. Okay, and you could probably tell by the way this problem looks, this is really going to be based on resonance. All right, so we should draw the conjugate acid. Okay, so here's an O minus, and if we draw through the rest of this molecule, okay, we're going to be able to move this minus charge onto here and kick this guy around. All right, so I'm not going to draw those structures. I think there's probably 3 other resonance structures because you can move each of these double bonds. But okay, that's not the most interesting thing in the world. It gets a lot more interesting once we add something else on. All right, so how about we draw this guy over here? And then just like last week, I'm just going to draw what NO2 is because I have the feeling that it's going to get involved in resonance. Okay, so this nitrogen has a plus, it's double bonded to one oxygen, and then one of these oxygens is a minus charge. Okay, so we can kick this minus charge over here, move this bond down over here, and I'm doing a couple steps at a time here, but well, yeah, you can usually go from any resonance structure to another one just using some, like a bunch of double-headed arrows at once instead of like just one at a time. But how this would look one at a time is you put the double bond down from the oxygen and kick this one over to this next carbon over. Okay, but I'm just skipping that and I'm just going, okay, I'm going to move it one whole bond over and kick this double bond down to here. Okay, and then what that does is it kicks this double bond over to the oxygen. So now if we draw this out, maybe let me draw it over here just so that I have a bit more space for the next one. Okay, we have this double bonded oxygen, and now it goes down. This double bond stayed, this one got moved. Okay, we made a double bond to the nitrogen, and here we go. Both minus charges, but that's okay. This nitrogen still has 4 bonds. So, okay, it looks like it's still plus. Okay. And actually that works out because we had a minus charge, and a plus charge. And now final structure, minus, minus, plus again. Okay, so we didn't make or break any charges. Okay, that's a good check. And we were able to resonate onto this NO2. Okay. Cool. That works nicely. All right, what about this other one? Maybe there's something that we were totally missing and this one can work even better. Okay, let me draw it exactly the same as the last one. Whoops. Okay, not exactly because it's a different molecule. Here we go. So there's a plus charge there, and then, okay, let's put a minus. Great. Let's kick this minus charge down, move this bond. I'm going to move it onto that carbon now. Okay, so let's see what the resonance looks like. Here we go. Minus charge was over here. Draw this structure out. Okay, and now, okay, what can we do with this minus charge? Well, we can move it back over here, although whatever, that's just going to get us the same place we were earlier, right? No progress. Now we can move it here. Oh, but we have to push this double bond along, right? There's no way to move the minus charge to make a double bond with this nitrogen. That means this would have to go over here. Okay, right, so if we draw this whole thing out, right? Oh, there's a minus charge over there, but our NO2 is untouched. That's no good. Okay. This is, for all intents and purposes, this is the same as if we just didn't have the NO2 at all, right? Because otherwise we could just loop and we can put this minus charge over here or over here. And it's for all intents and purposes the same as if we didn't have any NO2 here at all. Okay. Yeah. Although I guess I should mention one of these molecules doesn't have an NO2 here at all. So there must be some difference between the two of these because we're being asked to rank their acidity. And, well, they're not going to ask you, oh, just tell me that they're the same, right? Different molecules, there's always going to be something that's very slightly different that's going to affect their acidity. All right. So what is it in this case? Well, this NO2 is an electron withdrawing group, okay? It pulls electrons away. The way you can see that is because, well, here in this other case, it took electrons. It actually by resonance is able to pull electrons away, okay? No electron donating group is going to be able to do that. So this has to be an electron withdrawing group instead. Even though here it can't get involved in resonance, well, it's still inductively pulling electrons away, which still inductively makes the molecule slightly more acidic. Okay, so we can compare these two guys over here by inductive effect. And then these two, well, we drew it out. This middle one has a really nice resonance structure. Okay. So here we have resonance. Okay. So we know that this is because it has resonance, it's the most acidic for sure, right? So if I'm going to label them 1, 2, and 3, well, 2 is going to be most acidic, no doubt, because it has resonance, right? And then 3 is going to be more acidic than 1 because it has the inductive effect. So 2 is more acidic than 3 is more acidic than 1. Okay. Oh, I got a chat message. Why can't the NO2 get involved in resonance? Yeah. This is something that really gets glossed over when talking about resonance. And, well, I mean, this is like a confusing kind of concept. It's like always confusing because sometimes to see whether something can get involved in resonance or not, you just have to draw out the resonance structures, right? And every once in a while in lecture, especially like later on in the course, this is like a minor pet peeve of mine, and I imagine if it's a pet peeve of mine, it's a pet peeve of a lot of people for organic chemistry. There will be times where it's just like, oh, there's a nice resonance structure, it exists, or like, oh, this structure can't resonate. That's it, right? That kind of sucks. So the idea here is that sometimes things will look like they can resonate because you have double bonds and they're all kind of conjugated with each other. Conjugated meaning that you can move double bonds over. But the way that the placement of those bonds lines up is that you can't move like a charge down the line or onto one of the things that's along that line. Okay, that was vague as hell. So why don't I actually show you what I mean? So, okay, we move this minus charge down to over here, this carbon, right? And now if we move this minus charge onto this double bond over here, this bond, it has to push, well, that's the only place it can go, first off, unless it just goes backwards. But we don't want to go back, we want to actually say something meaningful here. So it's going to go forwards, right? We're going to push it along the chain. And while we're doing that, well, this double bond has to move somewhere, okay? The only place we could have pushed this along the chain is onto this bond in between, and this double bond has to go somewhere. Well, the double bond can't go, we can't do this, for example. Okay. So, well, let's say we move this double bond onto here. Let's say we can't have moved the bond over to here. Okay, because of, well, one of the most, like, I mean, this is like a common place of error, is that if we were to do something like that, right, this arrow, I'm showing what I had done, right? Look at this carbon. 1, 2, 3, 4, 5 bonds. Okay. No, absolutely not. No 5 bonds. Okay, you can't do that, right? Yes, there are things that can make 5 bonds. I don't think this is something that you will need to do. Okay. And when it comes to carbon can't make 5 bonds. Okay. No way. Okay, there's no point at which carbon can make 5 bonds. If you're a physical chemist, I'm sorry, I'm sure there's some crazy theoretical world in which carbon can make 5 bonds, but whoops. For the sake of this, can't do it. Okay. So this double bond over here has no choice except to get pushed over to the next carbon, which is what I had drawn over here. Okay. The placement of this NO2 just means that, I mean, regardless of what you're going to do, you can't get the minus charge onto there. Okay, let's say we move this guy over here. Well, okay, maybe it can move onto here, right? Or if we move it over to here, well, we can get a minus charge there, right? But there's 6 carbons, and it's like a cyclic number, right? So there's like every time we can only move this minus charge over by 2, right? So okay, we can move it over by 2 to here, over by 2 to here, and over to by 2 to here. If you remember from last week, we had a resonance structure with 7 carbons, and I said, oh well, there are 7 carbons, and you could see that the charge can land on every single carbon along the way. Okay, because every time we can move it over by 2, and well, 2 doesn't divide nicely into 7, so okay, we can get every single carbon that's along the chain or along the ring, right? But here we can only get these set number of carbons, and this NO2 doesn't really land on any of these, so we can't really get it involved in resonance. Okay, oops, oh, there's another chat over here. Sweet, okay. Cool. Well, that covers all of those, right? I bring this up again because, like, again, acid and bases is like, you cannot escape it. It will come up again and again and again, and it will haunt you. I you know, maybe you really love acids and bases. I know that like this early in the course, I hated these problems. I could not do them. I couldn't figure them out. I thought, like, what the hell? How am I supposed to know that, let's say, NO2 is an electron withdrawing group, right? Like, at some point in the past week or two, somebody has just said NO2 is an electron withdrawing group, and you're just like, oh, cool, I guess, right? Like, I didn't know that. I certainly didn't when I was taking the course. So maybe at some point in like the recorded lectures or Professor Calendar's like reviews, she described those and talked about them. But well, hell, I didn't know. I had no idea. Yeah. Okay. It's one of those sorts of things where, like, as you take the course, you will definitely be developing an intuition about it, because you will be seeing it so often and often again, and like this concept of like an electron withdrawing or donating group, or maybe not so much like inductive effect. It doesn't really come up that much anymore. But like resonance also. These are such kind of prevalent ideas that it will become more familiar. Just this early in the course, they kind of expect you to pick up on it fast, and like I totally didn't. But don't worry if these problems are still a little like opaque or obtuse or whatever the word is, right? Yeah. Okay, cool. How about we actually do this week's workshop? Let me draw in a little bit of lines. So this week, I won't review too much because, again, this concept of like these structures, like the Newman projections, doesn't come up way more in the course. Like, this is kind of the last time you'll probably see them. Maybe in like 1 or 2 rare problems way down the line where it's like kind of necessary to understand how the problem works. But I don't know. I haven't really seen it that much. But the point is that if you have a molecule that looks like this is like the absolute standard, right? Actually, you know what? Why don't I really go wild and throw in a methyl here, right? So we have something like this, and well, the idea is there's a bunch of hydrogens everywhere, right? So there's hydrogens here, and then there's a hydrogen here, a hydrogen here, and these are all living in 3D space, right? So what I should really do is draw like this hydrogen coming out of the page, and then this one's, sorry, this hydrogen, the first one with the wedge, this like solid thing over here, which we call like a wedge usually, that's coming towards you, okay? So I just did that. So to you, it looks like it's coming away from you. If you're sitting here, it's coming towards you. There we go, okay? And then this dashed line over here is one that's coming away from you, okay? It's going into the page. Okay, right. And then over here, yeah, we could do the same thing. Well, why don't I make this guy as a wedge? Okay. And I can make this girl over here as a hydrogen. It's going into the page. Okay. These live in 3D, right? And you might get a question that's like, or you might have gotten a question that's like, okay, let's say that you are, this is like the standard like eye drawing. Let's say you're looking this way and you're looking along this bond axis. Draw this structure as a Newman projection, okay? The way that this works is you take whatever's in front and you draw it out, okay? And so you kind of want to take it from what's on the page and rotate it by 90 degrees so that you can see it head on. Okay. So if I do that, I'm going to take this methyl and move it to the right. So that methyl is going to move to the right. This guy will stay up top because it's like a flagpole. It sticks up, whatever way you rotate it, it's the same. And then this hydrogen will be on the left now, okay? This is what we see in the front. And then we draw this big circle to talk about what we see on the back, okay? And what we see in the back is that we had this hydrogen, okay? Now I'm not going to draw the lines all the way back to the back. This hydrogen was back here. We had a second one sticking out the back. And then up here, we had another methyl. Okay. So this is an eclipsed conformation. Okay, this guy is eclipsed. And this is kind of uncomfortable because you have these hydrogens bumping into each other and you have these methyls bumping into each other, right? But we can kind of twist. Okay, we'll leave everything up front as is. And now we can do this thing over here. Okay, and well, this is staggered. All right, and these methyls, since they're 60 degrees away from each other, these guys are gauche. Okay, and if we wanted to rotate this guy even more, well, we can move the methyl down here, right? Draw the rest. You could tell that, okay, my drawing quality is getting worse and worse as I'm moving through this quickly. Okay, we can move it like this, and then we have them opposite to each other. Oh dear God, yeah, I can't even remember from earlier what it was called. Nobody's gonna ask you the name of it, right? Someone I'm sure remembers. If you throw it in the chat, I'll be like, damn, I totally forgot. Let's see. Anti, yeah, okay, thank you. Oh my God, yeah, there's a simple name, right? Yeah, so these guys are anti to each other. Okay, these methyls. Okay, we're really focused on the methyls. Oh, but look, these two guys are gauche anyway, right? Yeah. So we didn't get that far anyway. But here we had two gauche interactions. Oops. So here we had two gauche interactions, and now we have an anti plus a gauche. So anti plus gauche is better than two gauche. So I'll write more stable or more favorable. Okay. And in general, in organic chemistry or in chemistry in general, when we say more favorable, we mean lower energy. Okay. There's an energetic cost to having these methyls bumping into each other. So here, this anti, because we have one of these being anti, it's bumping in slightly less, so it's more favorable. It's nicer and it's better that we have that. Okay. Oh man, it's really throwing me all over to the place today. Here we go. Okay. Yeah, it's called anti. Okay. So someone also asked, does it matter which you choose to draw as a wedge, dash, or line, as long as you account for all these positions? So yes, it does. Okay. And the reason for that is a little bit specific. In this molecule, I should add also, it doesn't. Okay. In general, though, it does. And you will get to this very shortly in the course. I think as in this week, you will be covering this topic. And this is like the true the true pain of organic chemistry 1. This is like the if you're not like a big spatial thinker, like you can't think in 3D in your head, right? Um, this is like a real pain. Um, but the point is that if we drew a molecule that looks like this, so let's say we have, I'm going to go with what we had earlier, but make a slight modification. So if we draw, let's say, let me put an OH here and then leave everything else the same. Okay. So I can draw this wedge. Okay, and here's a dash that goes to this hydrogen. And let's see, what else did I have? Here we go, right? Here's an H and here's an H. These two H's, it doesn't matter where you put them because they're the same thing, okay? Here though, this does matter because on this carbon, we have 4 different substituents, okay? And what this means is that this molecule, and if I drew this molecule, these things are different. These are not the same molecule. Okay. They look the same, right? They really do. You would think like, okay, I mean, they both have this hydrogen alcohol and a methyl and an ethyl group on there, right? Like, how are they not the same? This is like a very it's taken me a long time to get used to this also because like um they really do seem like they're the same, right? You could write the same molecular formula for them. They have the same atoms in them. They're connected. The atoms are connected to the same things. But the fact that this OH is in a different spot than this OH relative to everything else on that carbon, that makes it different. Okay. What we would say is, and this is getting a little bit ahead, so these two molecules are called enantiomers. Okay. And there's this idea here, which is that these two molecules have what we call mirror symmetry. Okay. Meaning that if you took this molecule and you looked at it in a mirror, then it would be this molecule. Okay. Oh boy. How exactly does that work? Well, the idea behind this is that no matter how you draw this molecule on the left here, you can't draw it in a way that it is exactly this molecule. One might say they're not superimposable. Okay. But if you took this molecule and you flipped it, and we could actually go through the exercise again. This is what will come up this week, but I figured since it comes up and we're going to talk about it anyway, we might as well now. So if you took this molecule and you flipped it and took it through a mirror, which I'm putting here through a dashed line, okay, I'm going to do step by step and I'm going to draw it exactly like a mirror. Okay, here we go. We're going to make this guy a wedge. And now, there we go. Okay. And now if I take this and I take this molecule, now this thing is set, right? I'm not doing anything with it. I'm not changing or making or breaking bonds. Now all I'm doing is I'm just taking it and rotating it in space, okay? So I have this molecule, and I'm just rotating it. That's it. No, not mirror anymore, right? Now we rotate it by 180 degrees, okay? And what that means is what it looks like. This OH that was coming out of the page at us, or here we go, that's coming towards us, right? If we flip the molecule around, that OH is going away from us. Okay. So over here, now this OH is going away. Opposite for this hydrogen. Okay. Earlier it was going away from us. Now we flip, it's coming towards us. So here we go. There's a wedge. And well, the rest of this is okay. It doesn't change, right? It's just an ethyl group. I can kind of say that because, well, there's kind of a trick or a rule here, which is that if a carbon has 4 different substituents, then it's one of these places where you can get this issue happening. And none of the carbons over here have 4 different things, right? This carbon has methyl, this whole big stuff, and 2 hydrogens, and this one over here has carbon, 3 hydrogens, right? For all intents and purposes, those hydrogens are all the same. So we're not worrying about this part. Okay, we can treat it as just being mirror invariant, which is like a really complicated way of saying if we put it through a mirror, it's going to look the same. Or we can draw it to look the same at least. Okay, so anyway, now that we flipped it, we could see, okay, yeah, we really did get that the mirror of this guy on the left is if you rearrange these bonds. Okay. In fact, we could have changed any of these bonds. We could have changed that methyl and the ethyl. Okay, we could have changed this methyl and the hydrogen, flipped those positions. And any of those would have changed to the mirror. Okay, we would have had to rotate bonds and things would get a little bit more complicated in terms of like keeping track and not making mistakes. But, well, you know, we didn't have to do that. Okay, right. So yeah, we get this kind of issue happening. This is a long-winded way of saying in the chat here that it does matter whether you draw a wedge or dash. So just to go back to the earlier example, I had to check the chat again just to make sure I wasn't totally going off on an unrelated tangent. In this molecule, none of these carbons have 4 unique different substituents, okay? This one up in front has methyl, hydrogen, other stuff, right? But the fact that we have 2 methyls means we can stop there, okay? You can't have this sort of mirror symmetry with, or you can't have like enantiomers at that carbon, okay? And over here we have 2 hydrogens, so this one too, it's also safe, okay? Just to throw an extra term in here and make it more confusing, we would say that this molecule is achiral, meaning that you can't draw, it doesn't have any of these carbons where it has 4 different substituents, okay? Whereas this molecule down here, this guy is chiral, okay? The point is, in general, it matters whether you draw a wedge like this or a dash. Okay. In general, it does. Whew. Okay. Cool. That kind of hits at the most of this like section, right? Yeah. The big idea here is that you can draw the molecules in this way by looking along a bond, and you know, anti-interactions are better than gauche interactions. Gauche is bad because they hit into each other. Anti is fine. Okay. Oh geez. Oh, it really is really throwing me around. Okay. I zoomed in really close. Here we go. Okay, maybe one last note about these sorts of things. This is like a small note. Every once in a while, you might see someone draw Newman projections of a ring. Okay, so now, okay, you've started getting used to these guys, right? Because you have, like, you can have this stuff over here, right? So this guy up here, remember, is called axial, and this one over here is equatorial. Easy way to remember that is just equatorial lies along the equator, right? So over here we have this H that's kind of sticking up, and we have one that's sticking down. You always, whenever you're in chair conformation, there's always something that's like a flagpole up or flagpole down. I guess you don't normally have flagpoles that face downwards, right? But there's always something that's vertical up or down. And then the other one has to be at, this is tetrahedral, right? So the other one has to be at kind of an angle, right? So one of them is always up and always down, but it's up like a flagpole here. So this one is down kind of, right? It's a little bit down. It's not very much, okay? And then this guy over here, since there's one that's going straight down, the other one is like kind of up, okay? So again, equatorial, axial. Okay. Anyway, some people will draw this every once in a while looking along this bond and this bond. So what you could do is, well, now we got to draw things in because it's getting a little complicated. Okay. The hydrogen, hydrogen. So what you do is you can draw one carbon here, another carbon here, and draw Newman projections of both of these at the same time. Okay. There's circles. And let's see. Up front, this guy is on the left. So this is carbon. Let me move this little zoom thing that gets in the way. Here we go. There's carbon 1 and carbon 2. Okay. This is carbon 1 and this is carbon 2. There we go. There's a hydrogen going up. There's a hydrogen to the left, okay, because this is going away from us and this guy is coming towards us like a wedge. Okay. So this carbon comes over to the right, except over here, the carbon is coming away from us. So it goes over to here. Still in the front, okay? Now there's a hydrogen over here and a hydrogen sticking up. Now we can draw on the back, okay? There's a hydrogen sticking down like a opposite flagpole, right? And then there's this hydrogen coming up to the left over here, right? We have this carbon that's in between the two, it's shared, right? And likewise for this one, okay? It goes up to that carbon. All right. And let's see what were we missing over here? Well, there's a hydrogen that's sticking straight down. And then there's a hydrogen that kind of goes over this way a little bit. Okay. Every once in a while, you might see someone draw a ring like this. Okay. It's another helpful way of seeing it. Yeah, it's another way of drawing this stuff. You could draw each bond at a time, but hey, this works too. Let's see, we have a question. We often have the objective of determining the least energy or the most stable conformer. Is it consistent with resonance structures and the major contributor being the most stable? Let's see. Resonance structures and the major contributor being the most stable. So yes, although they're kind of separate things, right? So in terms of this conformation stuff, we're only dealing with double bonds. Okay. Let me close my parentheses here. Oops, there we go. Okay. So in terms of conformations, we're usually just dealing with single bonds. Okay. There are some specifics of conformational analysis that I don't know if have been covered in the class, but like there are a few specifics about it. So the thing that comes to mind is like there's this rule called like Brett's rule or something. So there's like so like an exception is like Brett's rule, which says that like it's very specific, but it says, and it's come up in the class before. So this is the reason I mention it. This is not just like me trying to confuse you more. So it says that you can't have there's no bicyclic system with a double bond. This is, it's really, really specific, but I'll show you what I mean. It's double bond on a bridge carbon. I don't know if that's exactly the right terminology. On a bridge carbon, where no ring, here we go, no ring has less than 8 carbons. Okay, this is the most specific thing in the world. Maybe you've seen this in the class or maybe it's been mentioned. The idea here is saying that like, let's say you have this ring, with 6. Oh, geez, I drew this one bad. Okay, here we go. Right, let's say you have this ring, and well, let's say that we threw in another ring, right? I don't know how many carbons that ring has. I just drew it in, whatever, right? Um, could we put, let's say, a double bond here, connecting to one of these carbons that bridges the two rings together? Well, we need to check, do we have enough bonds here, right? Is there some ring that we can count? Because there are 3 rings, right? There's this one, there's this one, and then there's the whole thing, right? This is the longer ring, right? Do any of these have at least 8 carbons? Okay, well, maybe we can count. Okay, here, 1, 2, 3. I'm going to count the longest ring because it, has the longest thing. So 5, 6, 7, 8, 9, 10. Okay, we can have a double bond there. All right. To give a counter example, we can have something that looks like this. Okay, and the question is, can we put a double bond here? And well, let's count the largest ring, which looks like the one that's flat on the bottom. So 5, 6, no, we can't. Okay. Maybe you've seen this before. I'm not sure if it came up in class. I know that it has in the past for me. And you will see structures that look like this. Or rather, you will see things that kind of look like this, just the double bond is somewhere else. And you have to be able to think, okay, can I do it here with the double bond attached to this carbon that bridges the two together? Okay. Anyway, the idea that's different is that resonance, you're moving electrons. Okay. So here you're dealing with double bonds too. You actually, to do resonance, you necessarily have to have double bonds or just a bunch of charges together. Okay. But if you want to move those charges, you're going to need double bonds. All right. But the idea is similar, which is that in resonance, there will be something that is the most stable because, well, it has the most favorable positioning of electrons, right? It fulfills octet. It's on the electronegative atom or something, right? Those things will be lower energy and hence more stable, so you have a kind of major contributor, right? With conformation, and maybe I should say, I'm going to hide this thing about Brett's rule and just move it up here, right? So with conformations, you're able to twist and bend your molecule a bit, right? So you can take your molecule, you could smush it, and you can flip it and do ring and chair and boat and conformations and whatever. Yeah, sure, right? But when you're doing that, there will be things that kind of bump together and clash together, right? Yeah, right. Like when you have a molecule that's just a triangle, right? Cyclopropane, okay? You have to bend those bonds a lot to be able to fit them together, right? That puts them under a lot of stress. So you have to put a lot of energy into to be able to bend them like that. It's not very stable, okay? Cyclopropane is really easy to burn. It lights on fire, like no problem, right? Whereas something like cyclohexane is really easy to put together, okay? All of the bond angles are exactly matched with what the actual molecule is supposed to have, okay? Like you don't have to bend anything, no problem, right? So the idea that's common between conformations and resonance is that some of the stuff will have lower energy, so it'll be more stable, okay? There are just some ways to position things and move things around that are more stable. The difference is that with resonance, you're usually moving electrons. Well, you necessarily are moving electrons, right? So you usually need double bonds. With conformation, we're typically talking about single bonds. Yeah. There's also a, I don't know, small or subtle difference, which is that with conformations, the molecule can only exist in one state at a time. Okay. So if you have cyclohexane, for example, it is at one time, it is either a chair or a boat. You are not going to have a cyclohexane that is both. you can't do that, okay? With resonance, you really have a mix of all of the different structures at once, okay? So we draw resonance structures to help us understand, because our brains aren't really good enough for this, but in reality, it's kind of in a mix of like all of the states at once, okay? All right, cool. Okay, anyway, oh, look, I've gotten to the end of the page here because, well, we've talked so much, but okay, that's good. It's good that we have anyway, right? This is good stuff for review. It's helpful and useful, and we also got to talk a little bit about what you're about to see next week, which is, whoops, which is it's a complicated enough topic as is, so we might as well just kind of get started on it early. Okay, here we go. Let's make a new thing. Let me zoom in. Okay, why don't we look at the problems for this week, actually? And I will pull up this week's worksheet. It's on the Canvas, right? So hopefully you're able to see it. I've uploaded it already. It's already on there, right? And okay, well, you'll see that the first problem, here we go. Here is the first of these problems, and you'll see, okay, it's a naming problem. And well, we're not really covering naming in this class, so how about we just skip it, right? I'm gonna pull it up here anyway, just to acknowledge that we looked at it, but like, we're gonna skip this one. Okay, I'm gonna move it all the way up here, and we'll skip. That's it. Okay. You don't cover naming. Professor Calendar, I believe, is following the same exact like sequence that Professor Molander does, and that doesn't normally involve naming. I think Professor Daly, who's actually not teaching a section of 241 this semester, I think he's put he has had naming on there before, but we don't really need it. Just for the sake of like, so that you have seen naming somewhat. If we take, let's say, A, okay, we'll actually do like one or two, but just for the sake of like, so you'll see these every once in a while, and you might as well have an idea of what they're doing. So when you're naming a molecule, you have, whatever's at the end here is how many carbons you have in the longest possible chain. So we have propane, okay, so that's 3 carbons. We're going to draw that, okay? And then 2,2-dimethyl means on the second carbon. So if we start numbering from any end, right, we're going to number from here. We start numbering from any end. On that second carbon, there is, well, on the second carbon, and on the second carbon again, we have methyl groups, okay? So there we go. Methyl 1, methyl 2. That's it, okay? So I drew this kind of ugly, but this molecule is really, looks like this, okay? That's it. Yeah, okay. If you were like really happy because I drew it this way, and you were like, oh, look, this whole thing right here, this is called a tert-butyl, right? That's like the name of this group. It's just like a common name for it. And you were like, oh, why don't I just call this tert-butyl methane? Well, that's not okay, because we have a longer carbon chain than 1, right? We can count a carbon chain that has 3 carbons at max. There's no way to count a carbon chain that's longer. This is not okay because, okay, well, we said methane, but really there's a propane in there. We have to take whatever's the longest chain. Okay, here we go. And for B, this one's slightly different, except now we just have this chloro and we have a methyl. The way that this works is that let's see, I think you arrange first by the position of the thing along the chain, and then you order alphabetically. Or let's see, in this case we have, well, 2,2-dichloro, so here we have our carbon chain. So here's 1, 2, 3, 4. On carbon 2 we have chloro and we have chloro, okay? And then on carbon 3 we have a methyl, okay? So if we were to go backwards and name this molecule, we'd have a chain with 4 carbons. Maybe let me do a different color. So we have this chain with 4 carbons over here, right? So 4C means butane, right? And then we have a methyl, And then we have chlorines. Okay, and let's see if I remember this correctly. You pick yeah. So I think at this point, once you're at this stage, you just go alphabetically, and whatever's first alphabetically, you put lower on the numbering. Okay, so you wind up doing 2,2 dichloro, and then this methyl, that means we put on the third, and then butane. Okay, all right. Well, that kind of goes through it, right? This next one, okay, cis 1 isopropyl 2 methyl cyclohexane. Well, we won't really go through it. Okay, it's a cyclohexane thing. For this class, since they don't expect you to know naming, there's not going to be a point where they give you something that's not totally obvious. Like if they give you like ethane, okay, you should know what that one is, right? But if they give you cis 1 isopropyl 4 methyl cyclohexane, I don't think they'll do something like that. And then in Orgo 2, I don't think they expect you to know naming. I know when I took it, there was like a test where they told us like, oh, what does chloroethane do in this reaction? And somebody raised their hand on the exam and was like, oh, can you draw chloroethane for me? And they were like, yeah, whatever. Because they don't care that you know how to name, right? It's not, Orgo 2 is not a class on naming by any means. There's a lot more that you cover in Orgo 2 that, well, they're not interested in naming at that point. Okay, so certainly like for this workshop, the worksheet that we're doing, I'm just going to draw these out for you, right? Because, well, yeah, it's not the point that you know how to name things, right? Yeah. Okay, here we go. 2,3-dimethyl-butane. Well, oh yeah, there's a butane, and okay, well, it looks like that. Okay. That whole discussion I did earlier with like enantiomers and things like that, it doesn't really apply to this molecule because every carbon you look at either has at least 2 hydrogens or at least 2 methyl groups on it. Okay. So, well, it doesn't matter how you draw wedges or dashes. But for the sake of us doing it, well, we can pick however we want to draw the wedges or dashes in that case. So why don't we draw this guy as a wedge and then draw this hydrogen here to back it up. And then I always suck at drawing wedges. I'm sorry. Here we go. There's a hydrogen. Okay, and we're going to draw looking along this axis. Okay. Normally the axis that you're supposed to draw it along is kind of straightforward and clear. Right. In this case, there's it's a butane. So there's like one interesting axis, and then the other axes are just like whatever. They don't really do anything interesting. Right. If we were to draw like this bond, for example, right, the front would just be 3 hydrogens. That's not interesting. Right. Okay, so let's say we do, right? We're going to take this molecule and we're going to rotate it this way, like 90 degrees, right? So this wedge over here is going to be on the right. This methyl sticking up is going to stay sticking up, and then the hydrogen is going to be on the left. A big circle. Here we go. Now this wedge over here, well, the way I drew it, it's eclipsed, right? It's like right next to this other one over here. So, well, we'll draw it that way, and then we'll put this other hydrogen over here, and then this other methyl will be sticking up like that. Okay, this is eclipsed. Well, that's not what we want. We just start with eclipse because, well, we know how to get to that really easily, right? It doesn't take a lot of, gymnastics in your brain to get to it, right? In this case, like literally gymnastics because you're moving the thing around and folding and whatever. Anyway, right? Okay, well then we'll just move everything over a little bit, right? We'll move this guy over here, this here, and oh, I drew this a little bit ugly, didn't I? Here we go. And then we'll draw, which of these is my nice pencil? Yeah, there we go. Okay, we'll draw this thing over here. Okay, so we'll nudge this over a little bit too, and well, everything in the front is going to stay. You can move the things in the front too if you want. I I prefer to move the things that are in the back, but well, it's up to you. Okay, there we go. This is what we got, right? Okay, and here we go. Let's just move everything over again. One, right? Bam, bam, bam. Just cycle all the things in the back. You don't even have to think about it. Just swap their places. Okay, so let's see. This hydrogen moved over up to here, and then otherwise it's just the methyls. Okay, repeat. Here we go. Circle in the back, everything in the front, we're not moving. Okay, methyl, methyl, hydrogen. Okay, and the question asked in order of increasing energy. Here we go. What do we have? So here we have, let's see, let me start drawing in a different color. Here we go. This is gauche. This over here is gauche, gauche, and that looks like all of the interactions we're dealing with, right? We're not counting the things with the hydrogens because those are, I mean, they're not as interesting. All right, what do we have over here? Gauche and gauche. Okay. And there's the anti, right? But we're just gonna count the gauche interactions because those are the ones that are really energetically unfavorable. They're the ones that really do us in. Okay. And now what do we have over here? We have gauche and gauche and another one. Okay, so there are 3 conformations, and if I label them 1, 2, and 3, just giving them labels so that it's easier. So this is, let's see, in order of increasing energy. Okay, so lowest energy, which also means most stable. Okay, well, this one only has 2 gauche interactions, so that's better, right? They're not bumping into each other all the time. Okay, so here we go. 2 is let's see, lowest energy is less energy, right? Because I'm talking about less energy and also most stable at the same time. So it's less energy than 1, which is about the same as 3. Okay. Yes, right. So in 3 we have this let's see, we have 1 anti-interaction, and over here we also have 1 anti-interaction. Yeah, it's the same. Okay. Cool. That's number 2. Any thoughts or questions? Oh, I just made this thing way smaller. Whoops. Okay. Something was in the chat. What happened? Do we need to know naming in later orgo classes? Oh, this was a question from a little bit ago. No, I don't really think so. So Professor Daly, I haven't had him, so I don't know. I'm pretty sure he does teach naming in the first semester, and he also, I mean, he usually also teaches the second semester of organic chemistry. There are other professors that also always teach the second semester of organic chemistry, right? It's not like next semester everybody's going to get stuck with Professor Daly. Yeah, so I know that he in the first semester teaches it. I imagine that if you came to the uh oh, maybe a friend or 2 of mine took it with Daly and said they had to catch up on naming, so maybe you might, maybe. Um, but if you don't have Daly, I don't think any of the other professors expect you to know naming. So, uh, you might not. Maybe I wouldn't worry about it for now, and later once you know what you're working with, then you can kind of decide. I mean, we don't know who's teaching it next semester anyway. When we eventually do, I'll be sure to give my comments on that because I mean I've taken the class, and I know people who have taken the class with like any of the professors that teach it, so I'll be sure to provide my insight. uh yeah, for now I really wouldn't worry about naming too much. I think since it's not something that Professor Calendar really talked about or mentioned, it won't show up on any of like the quizzes or anything. especially not because if a naming thing came up on the quiz that wasn't like absolutely totally obvious, right? Like again, cycloethane, right? Okay, or sorry, not that's not a thing. Chloroethane, for example, right? Okay, it's a chlorine. It's a single chlorine atom somewhere on an ethane molecule, so 2 carbons. Okay, right. That's not that bad. Yeah, but otherwise, I don't think they'll really mention, they'll really talk about naming or expect you to know it in this class for sure. Because, well, if it showed up on a quiz, I'm certain that there would be a flood of questions. That's like, I have no idea what this is, right? Yeah. Okay, here we go. Whoops. Let me copy and paste the next problem. Okay, copy as on web. Oh yeah. Chair problem. Yeah. Okay, this is one of those chair and well, it's really just a chair confirmation problem, right? And if you'll remember, during one of the recorded lectures, I'm sure this is like this is one of those things where you do it out once and then never again. uh, I'm sure they drew out the full like confirmations for or like the full Newman projections of a ring when you have an equatorial versus axial substituent, and they showed that like when you have something that's axial, you get gauche interactions, but when you're equatorial, you get anti-interactions, and that's of course anti is going to be better than gauche. So I think in every situation, I don't know if I can think of anywhere this isn't the case. Um, Equatorial is just going to be more favorable than axial. Okay, it's just an easy rule for the rest of your life. You can just remember that rule. Again, I can't think of a time when it's not. That's just not the case. Okay. So here we go. Here's our problem. Difference in energy between having the methyl group at axial versus equatorial is some number, right? Draw the chair confirmation where it's axial and show the two gauche interactions that account for this energy difference. Okay, well, we got to do it out then. There we go. Let's draw a ring. And, oops, a little bit ugly. Here we go. Let's just stick our methyl up here. Oops, let me draw it like a flagpole. Straight up. Okay, cool. Here we go. Okay, so there's that hydrogen. Oh, whoops. I almost drew 5 bonds. Don't do that. Here we go. Okay. And let's see. We want to draw the two gauche interactions that account for this energy difference. Well, it's always like a bit hard to remember which bonds you want to look along to do that. But if we want gauche interactions, then we want to see that this bond is gauche with this carbon, or this bond over here, so this carbon over here, right? So to do that, we're going to look along this bond right here, right? So, okay, let's draw everything that's out in the front. Why don't I fill in and populate the rest of everything else here? So there's a hydrogen that's sticking straight down and then a hydrogen over here. All right, here we go. Let's draw this red one. And everything that's in front. So here's a hydrogen. Here's a hydrogen. Okay, what's in the back? Okay, axial methyl. I'm just gonna write ring, make our lives a lot easier. And there's a hydrogen back there too. Okay. Oh yeah, there we go. Look at that. There's a gauche interaction. Okay, that's it. Right. We could see that if the methyl was here, then we'd have anti. Okay. That's it. You could draw the other one too. Okay. So this is why I did it in red, so I can pick a different color. Okay. You want to show that this guy over here is gauche with this. Okay. So now this is hard to draw, but let me draw it way back over here. So we want to draw our eye, and then it's going to look along that bond. Okay. Alternatively, you could have drawn the eye over here. Oh, that's such a bad angle. Okay, you could have drawn it that way too, and put this carbon with the methyl on it. You could have put that one front and center. Sure. You would have done it. You would find the exact same thing as over here, just maybe twist it around a little bit, but otherwise, you have the gauche. Okay. All right, here we go. Ethyl group is larger than a methyl. Difference in energy is also the same. Okay. Show why it's not less, or show why it's equally stable. Okay. All right, here we go. Well, let's draw the ring. Oh, okay, there we go. Oh, man. Okay, here we go. And, well, there's an ethyl group. Okay. I already kind of drew it in a way that it's a little bit suggestive here, right? This thing is going to just point away, right? We could do that, right? No, it's not going to bump into these hydrogens over here because, well, it's just going to stick out that way, right? There's no reason it needs to. Oh, whoops, wait. What? It's definitely not going to bump into that one. Here we go. It's not going to bump there, right, either. Okay. So let's say that we did it. What we'd want to do is look at this guy right here. Okay. Because that's where we can rotate along, right? We can just twist that way, no problem. And so that means we could just twist away over here, right? Every once in a while, you'll get these, let's see, I think they're called 1,3 diaxial interactions. So there are some examples where, like, well, this is an aside. This is an example. So let's say you have a structure that looks like this. It's got tert-butyl on there, right? And then you flip it. So, okay, we'll flip like this. Oh, draw it all the way out. Okay, so it looks like that. Well, you're only ever going to get this one. Okay, in fact, let me put it in red. You will never be able to draw this. There's no back and forth here. Okay, or for all intents and purposes, there's no back and forth, right? This equatorial, this axial position for this tert-butyl group is so unfavorable because it's so big, and there's no way you could twist it so that it doesn't bump into these hydrogens. It just doesn't happen. Okay, oops, oh, there we go. You really only ever get this one. Okay, it's only equatorial for all intents and purposes. Again, right? The difference in energy is so high between these two that you're never like, it's going to be in this state pretty much the entire time. Okay, yes, there's like thermodynamics and says like, okay, there's always going to be a tiny bit where it's in the axial position, but okay, I mean, yeah, right, for all intents and purposes, again, this is what you're going to have, right? That's just a brief aside, but here we go. So we're talking about the axial position up here, right? And we want to see that, okay, there's no interactions up here, but also this methyl group, this guy over here, it's not going to really interfere or bump, right? It's not going to get in the way. So we're going to look along this bond, and now this one's really confusing because we've got to rotate this whole thing that way if we want to look along it. Okay, so let me draw on this extra hydrogen, and we're going to flip this thing this way and then towards us also. So it's going to be like this thing is opening towards us. Okay, so why don't I actually draw this, and then I'll make a brief comment on it too in a moment. Here we go. Okay, so we did that, and now we've got what's in the back, right? So here we go. There's a hydrogen, and there's a hydrogen. Okay, and well, we could just stick this methyl back here, right? Yeah, we could just completely do that. Here we go. And then there's this hydrogen over here, and then there's this hydrogen, right? And so over here, this winds up getting us something that looks like this. Oops. I did not fill in anything there. Okay, here we go. Okay. Um, okay, well, we have a gauche interaction that we didn't have before, right? That kind of gets in the way. But no matter how we move this, we can move this methyl over to this position too, and we'll also have a gauche interaction. But the thing is, the question's only asking about the difference in axial versus equatorial, right? Um, this gauche interaction is built into the molecule, we might say. So if we looked along, our earlier bonds, right? If we looked along this positioning, well, this red is unchanged. Okay. This methyl is too far away to actually get involved in what's going on over here, right? Between this and up here. All right. And then this interaction here, maybe I could draw it when it's when this whole thing is equatorial too. So let me do a ring flip. Okay. And okay, well, we now have, let's see, this hydrogen like drops down. Oops. Oh, there we go. Okay. Wasn't letting me do anything for a moment. Okay. This hydrogen flips down and then this ethyl kind of moves down too. Okay. And well, we could do the same thing. We can just look along. How did I look along it last time? Okay, I looked from this part of the carbon. Okay. Well, you do the same thing. All right. Hydrogen sticks down, ring, ring, telephone. No. Here we go. Okay. It looks like that. And then over here we have hydrogen, hydrogen. That was a really cringe joke, guys. I'm sorry. Here we go. Okay. So hydrogen and hydrogen, okay, is next to the ring. It's next to it here too. And we have this methyl. Okay. So if we draw this in a nicer conformation, well, there's the ring in the back. There's this. Here we go. Okay. So we still have this gauche, right? It's always going to be there. We can't get rid of it. But we're only looking, we are, let me do a completely different color, right? So we are looking for the difference in energy between these, delta G, between these two, okay? All right. There's no difference in energy between these two. Wait, no. What am I saying? There we go. Right. So we are looking for, is it my pencil? No, it's not. This is. Oops, let me do it in green. Here we go. We are looking for delta G, difference in energy, right? And let me label it up here, okay? Difference in energy between axial and equatorial conformers. Okay. But this has nothing to do with whether it's axial or equatorial. Right? I just drew them the same. I just drew them for both axial and equatorial, and they have the same thing, right? Like, drew them for both, and they're equally stable. Or I should write, really, if I want to be fair, I should write equal energy. Along this particular bond. Okay? In that case, that doesn't, the fact that it's an ethyl group doesn't actually matter, right? It's the rest that matters. And the rest is exactly the same, right? Regardless of whether it's a methyl or an ethyl. So, well, delta G is the same. Okay. That is between these two, between axial and when it's axial and equatorial, or when it's an ethyl and a methyl, it's going to be the same, because all that matters is whether it's axial or equatorial. Everything else after that doesn't really matter. Okay. The exception being this small example I drew up here. Okay. So here, oh, oops, there we go. Here, it does matter what else is on there because of this 1,3 diaxial interaction. Okay. Slash sterics. We can also call it sterics. Sterics is when things are bumping into each other because they're too big. All right. In this case, that tert-butyl is too big and it just bumps into all those hydrogens. Okay. Here, we're not really getting that because we can just tilt the ethyl to point away, right? We just move it somewhere else. It's not going to matter. That ethyl can rotate around, no problem, right? You can think about this thing, this ethyl over here as being like a little floppy tail, right? And it can flop whatever way it wants as long as it doesn't bump into the hydrogens, which it can do. It's no problem. Okay. Okay. Let me check the chat, see if there's anything going on. Okay, there's a question. Okay. Let's see. Tert-butyl with twist boat is the most stable. It'll be okay to just generalize that for bulky groups like butyl to be equatorial for chain conformation, not getting specifics like twist boat. That's true. Yeah. Okay. So twist boat might be the most stable. Actually, yeah, that's probably. I imagine there's some small detail like that. So this is referring to specifically this small thing up here, right? Yeah. So it's very possible. In fact, this is like a small detail I just didn't remember about. Yeah, twist boat might be more stable with tert-butyl when it's just that bulky, right? Because that tert-butyl is just a huge thing. It's like a real pain to move around, right? But yeah, you could treat it as if it's in just chair conformation. In general, but most of the time things are going to be just in chair conformation. Anytime you do reactions or write about some interesting stuff, you're going to be kind of focusing on chair. So for the sake of this, you could treat it as chair. Whenever there have been problems that come up that involve something like tert-butyl or something that looks like this, right? I kind of told this to you, but this is like a very common problem that you might see or that you might have seen about tert-butyl and like, oh, why does it not like to go, axially and stick right up? It's because it's bulky. So if it were to come up, it would be something along the lines of like, why is it in this form rather as opposed to this one? And there would be a bit of detail provided there. All right. Any other questions remaining? This last one, we're not going to write out as much, or yeah, we won't focus on writing out. This is much more of a conceptual question. This is also a very, very common sort of question. In fact, you might have already seen it. It wasn't. Well, I don't know where you might have, but it's no doubt it's in the book. It's probably in every book. It's just like it's a specific question, but it like asks the right concepts, so everybody uses the question, like no matter where you look. Okay, here we go. There's this molecule called trans and cis decalin. It's called decalin because it has 10 carbons. You can count them out. There's 10. Okay, dec for like 10. Yeah, one of them is cis and one of them is trans decalin. This kind of refers to naming, right? So the first part is identify which is cis and trans decalin. When you're talking about rings, cis refers to the fact that the things are pointing on the same side. Trans refers to the fact that they're pointing on opposite sides. Okay. So, well, this one, even though we're not really big on naming, let's just check anyway. We can look at either of these two rings. So how about we just look at this one? okay? And well, let's look at the other ring as if it were a substituent or two separate substituents or something, right? So, okay, over here, we've got this guy pointing up and this one pointing down, okay? One's pointing up and one's pointing down. Okay, that's trans. There's no need to think about it a lot more than that. Okay, here we go. Let's draw in the rest of these hydrogens. All right, this guy over here is pointing down. This one here is pointing down. Okay, this one is cis. Oops, I almost wrote trans again. Okay, that's cis. That's it. Okay, for naming. All right, cool. Which of these are the more stable conformation and why? Well, as they're drawn, over here with trans, we have 2 equatorial. Right? These guys are both equatorial because the hydrogens are going up and straight up and down. I don't know why I just zoomed me, but you know what? That's okay. Here we go. This one over here is axial, and this one over here is equatorial. So this is one axial, one equatorial. I don't think I need to explain in much detail. This axial one is better. Okay. So this over here, let me do it in red. Why not? More stable. Okay. The fact that it's 2 equatorial is better. Okay. Having that axial just kind of, it does you in just no matter what. All right. Okay, but let's see. One of them, this question tells us, in fact, one of these cannot undergo ring flip easily. And it asks why. All right. Well, we've already identified the most stable thing possible, right? You can't get more stable than 2 equatorial, right? What are you going to get? 3 equatorial? No, you can't do that, right? We have the 2 equatorial. This is already the most stable. No matter what, this trans conformation is going to be the most stable thing possible. But who knows? Well, we also know that with this cis conformation, if we could do a ring flip, it's still just going to be one axial and one equatorial. It's just the one that's axial and the one that's equatorial are going to switch. They're going to just swap places, right? So no matter what, this trans conformation is going to be more stable. Okay. Now the interesting question is, one of them can do a ring flip and the other one can't. Okay, so one of them is locked in place and the other one isn't. So which one is which? Okay. This is the point where as the I don't know, instructor here or the person leading the workshop, right? This is the point where I'm supposed to tell you, break out your molecular model kits and start playing with them. Okay. And you know, having this molecular model kit will give you the revelations and the insight that you need in order to answer this question. I don't like saying that normally. Okay. So I have one. Okay, anyway, so here we go. Okay, look. Here's trans, oh geez, okay. Here's trans decolon. Okay. This is 2 rings. You can see that there are 2 rings, right? I'm not with you in 3D space, so I have to be able to show this to you in 2D. So it doesn't help that much that I have a 3D object, which you can't see 3D either. Whatever. Okay. 2 rings. There we go. 2 rings like that. You can see them. Okay. You look along it this way, and it's trans. So if we look along this bond right here, okay, I'm trying to position it so that it's exactly in line with the camera. Okay, and here's one ring over here. This is one ring. And if we look at it, well, here's one substituent that's going down, and here's one that's going up. It's transdecolon. Okay. Look, I have another one that's also cisdecolon, and I didn't label them in any way, so it looks exactly the same, right? Oh, look, 2 rings. Okay, cool, right? Here's one ring over here. Well, let's say we look along this bond, right? One thing is going down, the other one is also going down, so it's cisdecolon. Okay, and now is the point where I say, okay, well, if you have one of these models, and if you actually do, maybe try building these because, this really might help you, and this is one of those problems where it's just like, you kind of do need to be able to actually do it. Okay, let's say you have this thing, all right? Well, we have this hydrogen up here is axial and this one's equatorial, all right? Let's turn it around, right? Let's make this one equatorial and this one axial. Okay, and well, okay, I did some flipping around and well, the one in the back is now axial and this one's equatorial. Okay, that actually worked. That actually worked pretty well, right? We did it, okay? If we weren't able to, well, then our model kit would say, no, it's going to break or something, and it's not going to be okay. Okay, that was cis-decalin. Remember. Okay, why don't I even write it down? We'll take notes while we do this. Okay. So this one. All right. Let me even draw a line. We'll make like a little table here. Okay. Okay. This one we could do ring flip. Okay. And I don't know how clear it was when I did it. A bunch of carbons just moved all at once, and then the whole thing flipped, like ta-da, right? Um, there's a lot of carbons moving around, and I'm personally not huge on these things because, well, I mean, it all looks the same, right? It's just a bunch of black plastic connected to each other, right? It's like kind of unclear. Okay, this is transdecalin. Okay, we have these two hydrogens. Both of them are axial, right? Okay. Let's see. Can we move both of these to be equatorial? Well, oh man. Oh, okay. My model broke. Okay, right. Not really. This is a case where I actually think drawing it on the page is better. Okay. So we have, let me copy it. Oh, I'm running out of space. That's okay. Here we go. We have this. Okay. And let's see. It looks like that. And then let's draw on those extras. Okay. Drawing this thing is taking years of practice, I promise. Normally, I've screwed this up every time. Okay. All right. So let's say we're looking at this ring over here. And now we want to take, so we're going to take this and move it up to be axial. We're going to move that to be down to also be axial. So if we draw that, well, let's draw the first ring. Well, flipped. It's flipped now, right? There's that first ring. Okay, there's that carbon that's going down. There's that one that's going up. And now we have to fill in, well, let me not make it easier for myself. It's going straight up, right? Okay, now we have to fill in one, or let's see. Okay, I'm gonna start numbering carbons now. Again, this is a really useful, really helpful tool. Okay, so here's carbon 1, 2, 3. Okay, let me just number all of them down the line. 6. Okay, here 1, 2. We have carbons 3. We can have carbons 4, and then 5 and 6. Okay, and let's draw them in. Oh man, that's not gonna work. Okay, there's no way you can do that. This is not it. All right, no, can't do it. Okay, so transdecalin, despite the fact that it's more stable, you can't ring flip it. Cisdecalin you can, transdecalin you can't. So you're kind of in this interesting spot where transdecalin is more stable because it has two equatorial interactions, but you can't ring flip it. You can't get two axial interactions. It just won't work. It's not okay. Okay. Nice. Okay, one new message. Here we go. Can you draw how the other one can flip? Yes, I can. Yeah, I could actually. Let me draw that out. I was kind of being like backhanded with my comments earlier. The modeling kits definitely can help. So the reason I was because for me, I don't find them. I haven't found them helpful. I think this is like, so for this like chair conformation stuff. This is like one of the few times in the course where the modeling kits are genuinely really helpful and useful. So then you might also find them really helpful for stereochemistry, which we talked a little bit about earlier with that whole mirror symmetry thing. And then there's one brief moment in Orgo 2 when you cover Diels-Alder reactions, which you'll don't worry about them now. The less you can think about them, the better for your health and safety. At that point, way down the line, you also might see them again, and you'll think like that might also be a time when having the modeling kit is really helpful. So I personally haven't found them super useful and helpful. I think like drawing this out on the page like this kind of really explains it clearly, as opposed to like oh, let me twist my modeling kit until it breaks, right? No. Yeah. So what does this one actually look like ring flipped? Well, okay, this is going to get complicated, right? There we go. Let's draw it just as it was earlier. So here we go. Draw this. There's a ring. Okay, there's one that's down, down. Here we go. And it was probably like that, wasn't it? Yeah, it was. Okay. And so what we want to do is, well, we'll flip this ring, right? That's what we know we're going to do. This ring on the left. We can kind of pick one of these two rings and focus on that. So here we go. Let's reverse the direction on it. So it looks like that. Same ring that we're focusing on. Okay, so now that was axial. So this goes to equatorial. Okay. And so in this case, there's a hydrogen here, right? Right. Let's see. So this carbon was facing up earlier. And so now it is over here facing down. Oof. This is gonna be a nasty one to draw. Okay. So this one, I should label them. Okay. This is why I should have labeled them, is because I now wouldn't have had this confusion. Okay. So this I will label carbon A and this B. Okay. Yeah, we're picking alphabetic labels this time. Gonna make things a little bit more interesting. Okay. This is carbon A and carbon B. Okay. You can see how this is gonna get ugly. Here we go. Let's go back to the color blue. Okay, this one was axial. Now it goes equatorial. There we go. Okay. Over here, this one was equatorial and this one was axial. Okay. This one goes down like that. Okay. It goes behind like that. Okay, here. I'm drawing this bond very long. Okay. Over here, I also drew these bonds very long, and I drew it to show that you can't do it. Now I'm drawing it very long because I don't have anywhere else to draw it. So it's behind the molecule like that. Okay. And let's see. Now we have, if we have this, right? Well, we can fill in the rest. So it'll look like that. Okay. So it will look like that. That is our ring. Let's see. Did I do this right? 1, 2, 3, 4, 5, 6. Good. Got it. Okay, we got that. Okay, it's 6 carbons. That is an ugly looking thing that I just drew. That's actually an abomination. This is why I mentioned earlier that like drawing these things is drawing this molecule in particular is just like takes years of practice. What we should actually do in order to get this like in a really workable kind of position, because this was already an awkward drawing, right? So what we should do is in some way we should rotate this molecule around so that we can draw it nicely. Okay. And I'm going to cheat because I know how to draw this. And I'm going to take this thing and rotate it up like this 180. Okay. Like around this axis. And what that will look like, and this is maybe the case where like the modeling kit will really shine through and it'll be worth the $15 you spent on it. Here we go. Okay. So now we're going back to here. Okay. Because we've rotated it, right? So these diagonals are now going to flip and they're going to be the other way around. Okay. Now this thing in the back, oh no, well, okay. Now this one in the front is in the front now. So it's up here. Okay. So it goes up there. Okay. And this thing is pointing down. Let's see. Wait, no. So here it was pointing down and now it's pointing up. Okay. The reason I I chose to draw this thing this way now is because here we had axial pointing down and equatorial pointing down. And now here we have them pointing up like this. Okay. Yeah. if we really wanted to do this nicely, we would move this whole thing over to here. And then I think we would be able to draw it in the same way as we drew this without anything clashing and bumping into each other. Okay. But, well, we have this, right? Okay, and now maybe it's a little bit better because we're not dealing with, well, yeah, it's a little bit better because we're not going behind the molecule. Oh, okay, right, fine. Yeah, so now we can draw this in, and there we go. There's the rest. Oh, okay, that was atrocious. Looks like that. Oh, that's not a lot better, is it? Yeah. The way that I've drawn it, maybe I've kind of put it in boat conformation here. No, it depends. It kind of depends on how you look at it. Like if this thing is so this thing is like this is coming out at you and this is coming like out at you again. It is chair conformation. There's just not very much of a nice way to do it unless you rotate this thing around all the way. But well, why the hell not? There you go. Okay, let's rotate this thing around. So now this guy is pointing up. This one is also pointing up. And then we fill in the rest of our chair. Oh, yeah. That's actually a chair conformation. Oh, my God. We made it. We made it there. Okay. Right. So let me fill in the circles where I had them. Okay, there we go. Right. So yeah, we could redraw it. And this is chair conformation. This is a really ugly chair. And I feel bad that I drew it this bad. I'm normally better about my chairs. All right, whatever. That's good enough, right? Okay, yeah. So we can redraw it. We can ring flip it. We can draw it. It took a hell of a lot of processing power up here to do it because I mean there's again we're drawing 3D onto a page, which doesn't really work, right? That's why I say this is one of the cases where the modeling kit really does make the difference. For this one particular case of this drawing cis-Decalin ring flip, they're really, really specific. Okay. The modeling kit may also, I mean, for each of you, your mileage may vary a lot here, right? You might find that the modeling kit really makes the difference, right? For stereochemistry, I think the modeling kit will make more of a difference than it did here, right? Or than it did for this whole conformation section, right? Stereochemistry is one of those few places where understanding this whole idea of mirror symmetry doesn't really happen until you have it in your hand and you smush them together and you see okay, there's no way to overlay one of these molecules on the other. You can't do it. Yeah, you'll see what I mean when you talk about stereochemistry this week. Yeah. Okay. I've talked for plenty long. How about I stop sharing?